continuing on with Chapter 2 lectures, and the next section, pretty much the rest of the chapter, is math-free. So those of you that are, folks that don't like math, you're going to breathe a sigh of relief. Those of you that do like math, you're going to have to grin and bear it. But getting into compounds, we need to sort of delineate two main types of compounds. Right? Most compounds fall into two categories. The first is called molecular compounds, or also referred to as covalent compounds. And molecular compounds or covalent compounds are a nonmetal bonded to a nonmetal. Okay, the non-metal part, non-metals. So we're talking about compounds that are made of elements that are entirely based in the upper right-hand corner of the periodic table, where it's all non-metals. The other type of compound that is most common are called ionic compounds, and those are when we bond a metal to a non-metal. Right? Now, metals tend to lose electrons. All right, and we talked about that in the previous video. So metals, when they make ions, they lose electrons and become charged. They make positive ions. Right? Positive ions are called cations. Okay, and the way that it's spelled, it's easy to assume that it's pronounced cation. That's incorrect. This is pronounced cation. Okay, like cat ion. And if you're ever wondering, if you get confused as to whether cations are positive or negative charged, pay attention to the fact that the T looks like a plus sign, so positively charged. Okay. The nonmetal in this situation, nonmetals tend to gain electrons, so nonmetals are the negative ion, and those are called anions. Right? And one way that I've heard to remember that these are negatively charged is a negative ion. Okay? So cations are positive, anions are negative. All right, so we have the two main types of compounds. We have molecular compounds or covalent compounds, which are nonmetal plus nonmetal, and ionic compounds, which are a metal plus a nonmetal. Now, formulas give the number of each atom in the compound. All right, for example, Dr. Lyon's favorite molecule is H2O. Right? That subscript 2 tells us that we have 2 atoms of hydrogen. Right? No subscript means that we have 1 atom of oxygen. Right? So the absence of a subscript just implies a 1. Okay? Anything other than a 1, we put a subscript to tell us how many atoms of each component there are. And this is why subscripts and superscripts are important in chemistry, in the writing of chemistry, because it tells us various things. Right? Subscripts tell us how many of each thing there are. Now we have two different types of formulas. Okay? We have empirical formulas, And empirical formulas are the simplest possible version formula that maintains element ratios. Okay, so for example, our H2O, there are 2 hydrogens for every 1 oxygen, so it's a 2-to-1 ratio of hydrogen to oxygen. So an empirical formula is the simplest form of that formula that maintains the ratio for that compound. Now we also have what are referred to as molecular formulas. Okay, and molecular formulas are the actual molecules. Right, now that may seem a little bit like confusing at first, because sometimes a molecular formula is the same as an empirical formula, but other times it's not. So for example, glucose has a molecular formula of C6H12O6, meaning that there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. That's the molecular formula. That is the actual molecule. The empirical formula we divide everything by 6, or a common multiple, whatever it happens to be, and we end up with an empirical formula of CH2O. Right, so thinking about that, so there are twice as many hydrogens as there are carbons or oxygens. Right, so the ratio of hydrogen to carbon and oxygen is 2-to-1. In the empirical formula, I have twice as many hydrogens as I do carbons and oxygens. So I have the same ratio, but it's distilled down to its simplest possible form. Okay, so in the case of H2O here that I have shown, the empirical formula and the molecular formula are the same. They both show the proper ratios, and they happen to be the actual molecule. The molecular formula is also the simplest possible version that shows the correct ratio. In the form of molecules, in reference to molecules like glucose, on the other hand, the actual molecule is not the simplest version that shows the same ratio. Okay, so empirical formulas and molecular formulas are different things, and we'll get into that using those a little bit later, I think in the next chapter. So I'm going to go ahead and stop this video right here, and we'll continue on with the next video talking about naming molecules, nomenclature.